Hello, Frank. Please try Gary a couple minutes earlier. Welcome, though. All right, let's get rolling for today's class. Good morning. Hopefully, you guys are all doing well, staying safe, and ready for the best class of the day. I'm looking for several people today. I'm looking for Alex, Alan, Joseph, Tristan, Nidal, and Frank. If you're here, please let me know. Again, Alex, Alan, Joey, Tristan, Nidal, and Faith. If you're here, please let me know. Another thing, Tristan, if you're watching this recorded lesson, please make up the post test as soon as possible. Go to Buzz, go to Regents Chemistry, Chemistry R. Brown, find the post test, please complete it. There's no password on there. If you don't do it, you're going to really hurt your quarter 4 grade. So please do so as soon as possible. All right, a couple other things to note. There is not much time left for the duration of school. So school year flying by. We are almost through a full year of virtual learning. A lot of you guys did really well in the post test. Nice job. I know a lot of you guys put your own effort in and did your own work. If you didn't put your own effort in and you somehow cheated on that test, you didn't get much out of the course. You're a good cheater, but maybe you didn't learn much in the course, which is, it's on you. But if you did well, if you did your own work, nice job. A couple things to note this week and next week. So this week there's final exams we should be aware of. You probably took some final exams already. The final exam offerings, there is final exams for business, English, phys ed, technology, and math. So you probably took your final exam in one of those, in those contents. Next week, the final exam schedule. You have the potential to have all these finals next week. You have business, ENL, math, phys ed, science, social studies, and technologies, one more, and world languages. So next week, you're probably going to have a lot of final exams. It's going to happen. So final exams next week. Your final exam for science, for chemistry, is next week. I am planning for next Thursday to have your final exam. What's on the final exam? It's probably going to be very similar to the post test. Besides, it's going to be anything from units number 1 through units number 11. So yeah, organic chemistry will definitely be on the final exam. And also we'll talk about nuclear chemistry. We'll go through that really quick unit in the next few classes. So those are both fair game for the final. Units 1 through unit number 11. The full year's worth of content. Again, that's going to be graded. It's a test grade. If you don't do it, you're definitely going to hurt your quarter 4 average for the course. Okay, Alex, please try to get here a few minutes earlier. So next Thursday, I'm planning for the final exam for the course. Any questions? Any questions? Last day of in-person class is the 16th, right into June. So 16th is the last day to be in person. The 18th and the 21st of June are remote days. And those days, there's going to be like basically a makeup days, but we're going to watch some videos on nuclear chemistry and organic chemistry. So it's more sign into class, watch those videos, and you're on your way. No assignments are going to be with that. Just figuring out chemistry and society. All right, here we go. Let's figure out what's happening for today's class. The quote of the week: accept no one's definition of your life. Define yourself. So you have one life to live. You have one shot to go out there and make the most out of your life. You control your destiny. You control who you're going to be, what you're going to be, what you're going to accomplish in your life. Mom, dad, grandma, whoever's raising you at home or whoever is watching over you is going to try to push you, but you have to have it within. If you want to make the most out of life, you have to have that drive, the will to do what you want to do in life. You have one shot to live your life. Go out there and make the most out of that life. Harvey Fierstein said that quote. Today's Wednesday, June 2nd, 2021. It's a day 1 today. We are going to wrap up unit number 10, organic chemistry today. We'll go through topic number 6, organic reactions. Really easy. 6 organic reactions we'll put in our notes. It's going to take like 10 minutes to go through the notes. We'll submit our notes for unit number 10, organic chemistry. Once we're done with that, we'll jump right into nuclear chemistry. It's a super simple unit. We'll go through that relatively quickly. So unit number 11, nuclear chemistry, we'll go through topic number 1, nuclear stability today. We'll watch a flick on nuclear chemistry. We'll go through some notes of all topic number 1, nuclear chemistry. And then next class, we'll go through some examples. We'll go through the exit pass on the topic number 1. You have the reference table. You have the video that I'm going to play today in class. Please open up their guided notes. Please open up the guided notes for unit number 10, organic chemistry. So again, this is the last day for organic chemistry. We will wrap it up today, move on forward from this unit. Let's see where we left off last class. So here we go, scrolling through this whole page. I'm going to go through this a little bit slower today because if you're missing something, you could rewatch this video, you could pause the video, and then you could fill out your notes. So there we go. Topic number 1, we talked about organic basics. We talked about hydrocarbons. Topic number 2, we went through homologous series. Topic 3, we went through isomers. Topic 4 was naming organic compounds. Topic 5 was functional groups. And topic number 6, which we'll go through today, is organic reactions. Before I jump into this, someone asked, are you going to tell us the post test grades? You should have access to your post test grades. It should tell you, if you click on test, you should be able to figure out what that test grade is. Let me know if you're having problems with that at the end of class. I'll help you out with that. Hey, Tristan, welcome. Hopefully everything's going well. Tristan, you got to do the post test. It's on Buzz. That's the main thing I need you to do today. You can rewatch this video if you need to. Tristan, on Buzz, if you go to School Link, go to Class Link, click on that. Log in into Class Link, find Buzz, click Buzz. Once you're on to Buzz, you log into Buzz. This is definitely our number 1 priority for today because they need to be submitted. Log into Buzz. Find Chemistry R Assessment Brown. Scroll all the way to the bottom. Find the post test. Please click on the post test and please complete it. 32 questions. Use your reference table. Use your scrap paper. Use pencil. Use a calculator. Please do that post test. Let me know if you have questions. That's for you, Tristan. You're the only one that's got to take in this class, so please do that. All right, back to chemistry. Here we go. Organic chemistry. Let's see where we left off. We talked about organic basics. We talked about organic compounds dealing with carbon atoms. Organic compounds are carbon atoms that are covalently bonded together. We said carbon atoms are very popular elements for organic chemistry because they have 4 valence electrons, and there's room for 4 more electrons within the atom. Organic compounds can make chains, rings, or networks. Organic compounds, carbons can bond with 4 other atoms. We talked about a single bond being a saturated organic compound. A single bond, for example, was butane. We named butane. We talked about a double and a triple bond being unsaturated. A double and a triple bond being unsaturated. We named one butene. We named one butine. We named both those organic molecules. We talked about hydrocarbons. We talked about molecular formulas before hydrocarbons. Molecular formulas we talked about. We said molecular formula tells you the types of atoms and the number of atoms in a compound. We looked at structural formulas, tells you the structure, the shape of the molecule. It tells you which elements are bonding and how many are bonding to. We talked about a condensed structural formula. A condensed structural formula tells you what is attached to each carbon atom. We said, oh, this first carbon atom, we have CH3. The second carbon atom, we have CH3. From the condensed structural formula, you can make a structural formula. That tells you which atoms are bonding, how many atoms are bonding, and what's attracted to it. We talked about the ball and stick models. It's a 3D representation of a molecule that tells you which atoms are bonding and the shape and the types of bonds. We talked about hydrocarbons. A hydrocarbon is going to be a hydrogen and a carbon in an organic molecule. We looked at the basic properties for hydrocarbons. We named hydrocarbons too. We looked at the prefixes on table P of the reference table. We looked at topic number 2, homologous series. We said homologous series were alkanes, alkenes, alkynes, A, E, Y, a single bond, a double bond, a triple bond, anes, enes, ines. Alkanes, we said, were single bonds. They're saturated. The ending is ANE. We looked at the formula for alkane series, which is CnH2n plus 2. We looked at some formulas. We figured out how to use that formula to figure out how many H's were in an alkane molecule, or a pentane, a butane, a propane, ethane. We figured out how to use that formula. We looked at an alkene. We said alkenes were double bonds. They're unsaturated. The ending for an alkene is ENE. We looked at the formula CnH2n. We figured out how to use that formula to figure out carbons and hydrogen atoms, how many are in each molecule. We looked at an alkynes, YNE, which is going to be an unsaturated triple covalent bond. We looked at the formula CnH2n minus 2. We also used that. We talked about an isomer. Isomer, same molecular formula, different structural formula. Same atoms, different shape. We looked at naming organic compounds. We named a straight chain organic compound. That was easy. You found the longest continuous chain of carbon atoms. We found the prefix. We identified the prefix. We looked at the ending. We went to see if there's a double bond or a triple bond in there. We named it accordingly to the homologous series. And then you numbered it from the side closest to the double bond or triple bond, or we numbered it for the side closest to where something was branching off. We did that. The day you had the AP test, we went through, we identified how to name branch chain organic molecules. We did the same steps. We figured out the longest continuous chain. We figured out what groups were attached. We figured out which homologous series it belonged to. We named the substituent groups. We numbered it. And then we named the organic molecule. We figured out the parent chain. That was the last thing. Then we figured out which substituent groups were attached. And we identified it in alphabetical order with a number indicating what was attached. There's the example there for you. Scrolling on down, we named organic molecules. You named pentane. We named 2-methylhexane. We named 3-ethylhexane. We named that one. Example number 4, we named 3-ethyl-3-methylpentane. Awesome. We also named 2,2,4-trimethylpentane. You named all those. We also had a name and drew a shape of the molecule, drew a structural formula for the molecule. This is the only portion of notes that does not have to be completed on your end. So when I do go through and check it out, this is the only portion you do not have to upload an image for. So this is the only portion you didn't have to do, but I did do this under the Elmo. We did all these structural formulas under the Elmo. Maybe you want to complete your notes and put those images in. I am not going to penalize you if you do not have them. Same thing for this one. Determine the following for the molecule. Could you name the molecular formula? Molecular formula, total number of atoms present. C1, 2, 3, 4, 5, 6. C6, H2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C6, H12. Could you name the condensed structural formula? C1, 2, so C2, no, CH2, then it would be CH, then it would be CH2, 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 CH3. That would have been the condensed structural formula. Could you do the empirical formula? Could you figure out a simplified version of the molecular formula? We said the molecular formula was C6H12. The empirical formula would be CH6. Find the common term. Could you do a structural formula? Could you do a Lewis dot diagram? That did not have to be completed. That was more for your reference. We talked about rings. We talked about organic molecules form chains, rings, and networks. We said cyclohexane, hexane. We looked at that. We looked at benzene. We looked at toluene. We also looked at naphthalene, two benzene rings fused together. We did all that. Last class, we talked about functional groups. We went through each functional group. We figured out the basic properties of each functional group. We figured out what made that functional group special or unique. And then we figured out how it was attached to each organic molecule. We looked at a halide. We said halides are F, Cl, Br, or I. If a halide's attached to an organic chain, it went in front, the name went in front of the organic molecule or the parent chain. We checked that out. We looked at alcohols. We figured out alcohols were an OH attached to an organic chain. Alcohol ending is going to be OL. We looked at that too. You drop the E and you add OL ending. We located the alcohol. We figured out where the alcohol is. There's an OH with an organic chain. That's an alcohol. Therefore, the ending has to be OL. We spent more time looking at alcohols. We said, oh, methanol. Methanol. Meth tells you one carbon atom. One carbon atom. There it is. The OL tells you there's an alcohol attached. What's an alcohol? It's an OH. We looked at ethanol. Eth tells you two carbons. 1, 2. And the single bond between them, the OL tells you an alcohol is attached. We looked at 1 alcohol, 2 alcohols, 3 alcohols attached to a parent chain. We looked at ether. What's an ether? An ether is going to have an oxygen smushed in between an organic molecule. Ether. I know we went through this relatively quick. Ether has an oxygen smushed between a parent chain. There it is. Oxygen in between 2 carbons. In between. There's an ether. Ether is the last thing listed. You have a methyl, you have an ethyl, ether. That's the example right there. Methyl, ethyl, ether. The name ending, ether is going to be the last thing represented. There's dimethyl ether. There's diethyl ether that we went through. We talked about an aldehyde. A lot of stuff with this unit. An aldehyde was going to be a C double bond with O and an H. A C double bond with O and an H. It's at the end of the organic parent chain. An aldehyde ending, we went through last time, we talked about, has the ending Al. You should be able to look at this and say, oh, it's not propane. Instead, it's, oh, Al ending. Drop the E and add Al. What's the Al represent? The Al would represent an aldehyde. Where's the aldehyde? Look on the reference table, functional groups. Oh, C double bond with O and an H. This Al tells you it's going to be an aldehyde. You check out the reference table, functional groups, you could figure out all this information. Find the aldehyde. Methanol. Oh, C double bond with O and H. With a 1 carbon atom. Meth is 1 carbon atom. All tells you it's going to be an aldehyde. Ethanol. Check out the next example. Eth is 2 carbons, and it's a single bond between the 2 carbons. All is C double bond with O and an H. Next example, propanol. You should be able to figure that one out too. We looked at ketones. What made a ketone a ketone? A ketone was a carbon with a double bond with O, smushed in between an organic compound. Again, the R's represent carbons on both sides. Example below, we have a C double bond with O, smushed between 2 carbon atoms. That is a ketone. So you're looking for these basic properties. The example we looked at was 2-pentanone. 2-pentanone. Think about this for a second. Let's break this one up for an example. 2-pentanone. Pent tells you the total number of carbons. 1, 2, 3, 4, 5. Okay, 5 carbons. And, let's do some blue. And tells you it's going to be a single bond between the carbons. Okay, single, 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 single. And then the O tells you it's going to belong to a ketone group. Color code in the system, you can really See this. Ketone is going to be a C with a double bond of O. C double bond with O describes the functional group for a ketone, smushed between the carbons. At carbon number 2, you have an O. So we had to number this. We number it from left to right because the functional group, the attachment here, is closest to the left. Carbon 1, carbon 2, 3, 4, and 5. 2-pentanone. Hopefully you can see that. Drop the E for the ending, and you add -one. Second example there for you. A few more examples. Organic acid. Organic acid is going to have a carbon, double bond with O, and an OH. There's a functional group. Carbon, double bond with O, OH. It's called the Cu group. If you're looking for that characteristic, you have a C double bond with O and OH at the end of an organic molecule. It's an organic acid. The example we looked at was propanoic acid. We found the C, the double bond with O, and then it's attached with an OH. A C double bond with O, whoops, a C double bond with O and an OH. That's an organic acid. The ending's going to be oic acid. You can see the ending, oic acid. There's ethanoic acid, propanoic acid examples outlined for you. Ester, we're getting closer, folks. Ester, C double bond with O and an O, smushed in between the organic molecule. Again, C double bond with O and an O, smushed between two carbons. That is going to give you an ester functional group. Find C double bond with O and another O, smushed between the organic molecule. That represents an ester. The name ending, drop the E and you add O8s, O-A-T-E. I think that was the last functional group we went through last class. Yes. So a couple more functional groups, and then we'll get the organic reactions. So maybe a few more minutes than 10 for the rest of this. So here we go. Next organic reaction we're going to analyze. Scrolling on down, so you can use your reference table handy. I guess I'll do split screen again. Reference table, get the functional groups out. Maybe you want to hard copy the reference table. That's fine too. But we're working our way through the functional groups. There's only 2 more remaining. So again, page 8, we're going to look at amine and the amide. So let's explore those functional groups. So again, if you're missing something in your notes, please complete it. Please watch this recorded lesson and complete it by Saturday. All right, next functional group. Hi, Joey G. Amine. Amine. So we talked about functional groups having some oxygens, some double bonds with oxygen, some nitrogens, also in the functional groups. The next functional group is the amine. Here we go. Filling that out. I'm going to cap lock, I'm going to bold, I'm going to highlight. So cap lock, bold, highlight. You know which one I'm looking at now. So I'll highlight the one we're on. Amine. Boom. This one right here in the pink font. So everything's referring to that text box over to the left on page 8. So here we go. Amine. This functional group for amine, what's going to make this functional group special is going to have a carbon with a double bond. Did I skip one? I skipped one. Sorry. This is my amine. Amine. This functional group is going to have a nitrogen attached to it, a nitrogen. You can see there, the functional group. What makes this group special? The nitrogen is smushed in between an organic chain, parent chain. N, R, R, R. That means carbon atoms are attached to this. There's a condensed structural formula for amine, CH3, CH2. CH2NH2. The name of this organic molecule, look at the reference table, is going to be 1-prop. One prop and amine. One propanamine. One propanamine. Let's think about this. Let's look at the structural formula below. So one propanamine, break it on down. Let's go. Break it on down. Prop tells you how many carbon atoms are attached. Prop. Okay, 1, 2, 3. Prop refers to 3 carbon atoms. And tells you single bond, single bond, single bond. And then the amine tells you which functional group is attached to it. The last name, the last part of that name tells you what is attached. Oh, amine. Oh, there it is on the reference table, page 8. Amine has to be the functional group with an NHH. So the functional group of nitrogen is attached here. Okay, there's a nitrogen with 2 H's. That is one propanamine. One propanamine. Amines contain NH2 groups attached to hydrocarbon in a chain or ring. The amine or organic derivative of ammonia is 1, 2, or 3 hydrogens are replaced with a hydrocarbon. Don't stress that. The naming of an amine group, you drop the E. So if an amine is attached, you drop the E ending. So cut the E. And you add amine. The ending is going to be A-M-I-N-E. You see that M ending is going to be a functional group of an amine attached. Second example, we have methenamine. Methenamine. Think about this process again. Meth tells you 1 carbon. There's my 1 carbon. And it's a single bond. Amine tells you there's a functional group attached. What's attached? Oh, there's a functional group. The thing that looks a little different is a functional group. It's a nitrogen with a couple H's. There's my amine group, methenamine. Oh, that makes sense. Let's check out ethenamine. Example 3, eth tells you the number of carbon atoms you have. Oh, eth is 2 carbons, 1, 2, and is a single bond between them. Okay, and then the amine is a functional group attached. Amine. Amine. Functional group, you have to have a nitrogen attached to it. There is a functional group attached. That's the thing that's growing off of the parent chain. Organic compounds can get complicated. Why? Because you could add these different functional groups to that. And the last functional group, amide. Amide. Last one here. Amide functional group. A-M-I-D-E. Very close to amine. Amide, you can see it's a little bit different. Amide, looking at it, you have a carbon double bond with O, but you also have a nitrogen attached to it too. So the difference is this one has an oxygen attached. Amine does not have the oxygen attached. The name of the compound we're going to analyze is going to be propanamine, propanamide. Let's check out the example below. Again, prop, break it on down. Prop tells you how many carbons, 1, 2, 3, and tells you single bond between them. And then the amide is a functional group. Oh, there's the functional group. It's got to be C double bond with O, then an NH. Let's see. A C double bond with O, and then an NH. Oh, that's a functional group right there. Most complex type of functional group that we'll see. There's an amide functional group. Name, drop the E, and you add the ending amide. A-M-I-D-E. Drop the E, add I-D, amide. So again, look at the last part of the name. That's going to help you out quite a bit. Second example, we have pentanamine. Pent and amide. Typo there. Please change that N to D. That should be a D there. Pentanamide. That was a typo. Pent tells you 5 carbons. Am tells you single bonds between them. Ide tells you the functional group attached to that compound. That is functional groups. Do I expect to see any questions on the final exam on functional groups? No, but I had the notes here and I wanted to really complete our notes. These are functional groups for organic compounds. Why I go through so quick? Just to complete the notes and so you saw it. I want to make sure you guys were exposed to this page of the reference table. So you can say, oh yeah, I know everything about the reference table. I'm aware of it. Maybe you're not that great of identifying it, but you saw it. Will there be questions on the final exam on organic functional groups? Probably not. There might be something like identify an alcohol. What's attached to this organic compound? An OH, an alcohol. But there's functional groups. All right, moving on forward. I know I went through that really quick. Next topic, topic number 6, we're going to analyze organic reactions. So organic reactions that we're going to explore, think about reactions that we already went through throughout the year. Reactions we went through a addition reaction where 2 things come together to make 1 compound. It's a synthesis reaction. You're combining those 2 things. We talked about a decomposition reaction where 2 things break apart or decompose to smaller things. A compound breaks off to smaller compounds, or a compound breaks off to elements. We talked about a single replacement or substitution. We said the element plus a compound yields a new element plus a new compound. We said a double replacement reaction is another type of reaction. A compound plus a compound yields a new compound plus another new compound. And we talked about redox reactions. What's a redox reaction? Leo says GER. You're losing electrons, oxidation, and you're gaining electrons, which is reduction. We talked about neutralization reaction, where an acid plus a base yields salt plus water. And now we're going to talk about organic reactions. Topic number 6. A few different reactions. It's going to go quick, though. Here we go. The first reaction is going to be a combustion reaction. The first reaction we're analyzing is combustion. Combustion reaction. When I see combustion, I think of heat. I think of energy. I think of fire. A combustion reaction. Almost all organic reactions will burn. When organic reactions burn, they will give off products of carbon dioxide and water. So the byproducts of burning organic reactions, most organic reactions, when you have that reaction burning, organic reaction burn, it's going to give off carbon dioxide and water. I did this reaction earlier in the year. When I did the whoosh bottle explosion. So again, the whoosh bottle explosion, I did this a couple of times throughout the year. I took a plastic 5-gallon jug of water. I took some alcohol. You didn't really know what the alcohol was back in the day, but I took some methanol alcohol. I put it into the 5-gallon jug. I transferred that from a liquid to a gas by spreading out the liquid. I capped it off, but then once I took a splint or a piece of wood, I burnt it. And once all the gases started to escape, it gave off this pretty big explosion, combustion reaction. What happened? I took the methane, which was CH4, methanol. I took that, I mixed it with air, O2. Once it burnt, it gave off a carbon dioxide, CO2, and it also gave off water as a byproduct. So when I did that reaction, I told you it smelled a little bit. That was the carbon dioxide. And also the water was produced as well when it reacted. Combustion reaction. An alcohol, organic compound, plus oxygen gas yields carbon dioxide and water. First reaction, combustion, done. Next one is a substitution or single replacement reaction. Substitution or single replacement. Second reaction, substitution or single replacement reaction. Substitution reaction involves the replacement of one or more hydrogen atoms in an organic compound with another group. The example below, you can see exactly what's going on there. You can see the replacement. If I'm not here one day, there's going to be a sub. They're going to replace me for the day. Substitution reaction involves in replacement of a hydrogen atom with an organic compound, with another element in an organic compound. You can see what's being replaced here in the situation. You have CH4 plus Cl2. So there's my CH4, methane, plus chlorine gas, Cl2, yields CH3Cl plus HCl. You can see what's going on. You have the Cl and you have the H swapping spots, switching spots, single replacement reaction. Those two switch spots in the reaction. Single replacement or substitution reaction. You know that one though. You've seen this reaction before. Reaction number 3, I'm gonna put it on the next page. This is an addition or synthesis reaction. Easy one. Saw this one before too. Addition or synthesis reaction. Addition reaction, you're taking two things, you're combining together to make one product or a bigger product. Addition or synthesis reaction. Adding one or more atoms at a double or triple bond in this situation. The example below, you have ethylene plus bromine yields 1,2-dibromo ethane. 1,2-dibromo ethane. You can see what's going on here. You're adding those two things together to make one product in the end. You're taking an unsaturated hydrocarbon and you're transferring it to a saturated compound. Double bond to single bonds. Addition reaction. Next one up, number 4. Reaction number 4 is esterification. Esterification is a process of making an ester. You can look at this word right here, esterification, and say, oh, it looks like ester. This is the process of making an ester. In an esterification, you're taking an organic acid and an alcohol to make an ester, to produce ester and water. What's an ester? You can check it out on page 8 of the reference table for the functional groups. Ester and water are produced. There is an example below for esterification. Acid plus alcohol yields an ester plus water. Esterification is a process of making an ester. Check out page 8 to figure out what an ester is. Or C, double bond with O and O, an ester. Flip back up in your notes. You can figure out what an ester is. Esterification. Esters are sweet smelling fragrances. So the stuff in your deodorant, the stuff in hand soap that make it smell so nice and sweet, nice fragrance to it that you like, those are esters in there. Perfumes, colognes, soap, stuff in your soap that make it smell good, and we talked about, those are esters. Next reaction, number 5. Few more to go. 3 more reactions. Reaction number 5 is saponification. Saponification. Awesome word. Maybe some of you guys have made this before. Maybe you did this reaction before. Maybe you do this and sell it at craft fairs, farmers markets. Saponification is a process of making looks like what word? Looks like soap. The process of making a soap. How do you make soap? We would have done this in real world Regents chemistry. We would have made some soap. We would have taken some Crisco, which is fat. We would have taken some sodium hydroxide, which is a base. We would have mixed those two things together to make soap and water. Those would have been the products. When a fat or oil reacts with an inorganic base, which is hydroxide, OH. So OH negative is going to be hydroxide. OH with a organic molecule is going to be an alcohol. So you have to differentiate between those two. This is hydroxide. To produce soap and water. So how do you make soap? Maybe you guys have done this before. If you go to a farmer's market, soaps are like really hot. They're always selling. There's really fancy homemade soaps that are always there. To make a soap and water. To make soap. To produce soap and water. I'll adjust that a little bit. Process of making soap. You're taking fat plus a base. You mix those together to produce soap and water. Oh, that's how soap's made. Pretty cool. Taking some Crisco. You're taking some sodium hydroxide to make soap. How do you get the sweet smelling soaps? You add an ester. Go up and add ester to it. How do you want your soap to smell? There's different esters that produce different fragrances. Different scents. There's an example below for an esterification. For saponification. You have a fat, Crisco, plus a base, yields soap and water. Next up, fermentation. Process of fermentation. You probably heard of this one before. If you live over in West Utica by Varick Street, you smell the fermentation process happening all the time. You smell it over there in Varick Street. You smell the beer or the products being produced over there, fermenting process. Fermentation is the process of making an alcohol. Fermentation, what happens? You're taking a sugar, you're adding it with yeast to make ethanol, alcohol, and carbon dioxide. The products are alcohol and carbon dioxide. The chemical process where yeast, you definitely need yeast for fermentation to occur. You have to take yeast. You have to take the yeast cells, secrete the enzyme with zymase and sugar and the glucose, sugar or glucose. With the 6 carbon chain, let me mess it up a little bit. Yeast cells secrete zymase and mix the glucose sugar with a 6 carbon chain. I'm going to change this to produce alcohol and carbon dioxide. Products here, carbon dioxide and alcohol. That OH there, that's the alcohol. How does fermentation process happen? You have to have a sugar. You have to have yeast. Once you have those two things together, it's going to make alcohol and carbon dioxide. If you never toured the brewery, spend the $5 this summer, go check out the brewery, get your root beer at the end of the tour. And when you go throughout the cellars, they're called the different floors of the brewery, you will smell the process of fermentation happening. You're going to smell carbon dioxide quite a bit. Carbon dioxide, you're going to be like, oh, what's that smell? It's carbon dioxide a lot of times in the cellars, especially when you tour the yeast or the fermentation cellar. There's yeast all over the place. There's going to be sugar substance, all sugar mixture throughout the place, and it's going to produce alcohol and carbon dioxide. The last chemical equation or reaction for organic chemistry is polymerization. Polymerization, a long word, polymerization. Polymerization is just like the addition reaction, but we're taking polymers. Polymers or plastics, think of plastics as that, as organic compounds. Polymers are organic compounds made up of carbons. Polymers made up of carbons of small units covalently bonded together. Hydrocarbons. Hydrocarbons, not carbons. Hydrocarbons of smaller units covalently bonded together. The formation of several polymers makes the process of polymerization, or it's called polymerization. So several polymers together is a process of polymerization. It's just like addition reaction. Instead, you're taking two hydrocarbons. Okay, there's an organic chain plus another organic chain. So two hydrocarbons, two organic chains added together to make one really long organic molecule. So you're taking two organic molecules, adding them together to make one long chain. All right, folks, that is it for unit number 10, organic chemistry. I know I went through these reactions quick. Will organic reactions be on the final exam? No. Again, I threw this in there just so you guys had it completed. These organic reactions I would overlook. I would not look through these for reviewing for the final. So chemical reactions, done. I wouldn't stress about this topic on the final though. Good to be aware of how things are created. Boom. All right, that is it for organic chemistry. If you're done with it right now, you can share it with me to jebrown@uticaschools.com or .org. If you need more time, you can watch this video, you can record anything that you're missing, and you can submit to me by Saturday. If you have a hard copy, I'll take that too. That is it for organic chemistry. Close the door, unit number 10, done, over with. Now we're picking up with next topic, which is going to be nuclear chemistry. So next up on the page, our Google Classroom page, we have nuclear chemistry, unit number 11. To start off this unit, I'm going to play a YouTube flick on Crash Course on nuclear chemistry.
Apparently, it can turn you into a superhero or into Apparently, it can turn you into a superhero or into a mutant zombie. It's the plot device for probably half of the sci-fi movies made in the last 60 years, and it's even the name of the song that welcomes you to the new age. To the new age, welcome to the new age. Presumably this new age occurring after some kind of apocalypse. As principles of chemistry go, few figure more prominently in the popular imagination than radioactivity, but at the same time, few are as completely misunderstood. Most people think of radioactivity as just something that mutates genes and melts faces off. And yes, some forms of radioactivity can do those things. But all the more reason to understand it, right? And also we can harness it to produce lots of electricity to fuel our rock and roll lifestyles without contributing to global warming, though, as Fukushima has taught us, it comes with some of its own problems, which we'll explore more next episode. Before we get into the nuts and bolts of nuclear chemistry, like nuclear fission and why it's so awesome, as well as fusion and why it's so hard to do, we'll first get to know radioactivity. What it is, what different kinds there are, and why you don't really need to fear it. At least, you know, not all the time. So, radioactivity doesn't actually have a lot to do with chemistry in the sense that we've been talking about for most of this course. Chemical reactions happen when an atom's outermost electrons do stuff, and the protons and neutrons and even the inner electron shells are usually completely unaffected. But the protons and neutrons are still part of the atom, of course, still part of the chemicals, and their interactions are important. When protons and neutrons get directly involved in reactions and their numbers do change, huge amounts of energy can be released, far more than by the transfer of electrons that we've learned about in other reactions. When these changes happen to the nucleus of an atom, we rather logically call their study nuclear chemistry. Now, it's probably occurred to you already that changing the nucleus of an atom can completely change its nature. Protons are the key to an atom's identity, so any change that affects the number of protons will turn one element into a completely different one. An alchemist's dream, right? Lead to gold. So as you might expect, that's not something that usually happens in a typical chemical reaction. The same can be said of that other component of the nucleus, neutrons. Atoms of the same element that have the same number of protons, but different numbers of neutrons are isotopes. So changes in the number of neutrons in an atom create different isotopes of the same element. Both of these kinds of changes, changing one element to another or changing one isotope to another, are known as transmutation. And it is indeed possible to transmute lead to gold. It's just so ridiculously expensive that the tiny amounts of gold produced could never pay for the process. But the very fact that it is possible should clue you in that nuclear chemistry is an entirely different flavor of chemistry sauce. Though, as with non-nuclear chemistry, the changes that take place in a nuclear reaction all come down to the atom's desire to have what we all want in life: stability. Just as atoms are most stable when their outermost electron orbitals are full of electrons, certain combinations of protons and neutrons make the nucleus more stable. And just like when an atom gains or loses or shares electrons to stabilize its outer shell, when the numbers of protons and neutrons aren't ideal, the nucleus releases some of them to try to reach a stable configuration. When a nucleus decomposes in this way to form a different nucleus, that's radioactive decay. And just like with other chemical reactions we've talked about, we need to know more about a nuclear reaction than just what's reacting and what's being produced. Probably the most important thing to learn is how much of the product is being made and how fast. Now, you've heard of half-life. It's the measurement that tells us just that: the time it takes for exactly 1/2 of the sample to decay. Different nuclei have different half-lives. By knowing the half-life, we can calculate how much of a sample will be gone in a given amount of time. For example, the half-life of phosphorus-32 is 14.3 days. So if you start with a 100-gram sample, after about 2 weeks, you'll have 50 grams left. After another 2 weeks, half of the remainder would decay, leaving only 25 grams of undecayed phosphorus, and so on. Now, you might be asking, if radioactive elements are always decaying into more and more stable isotopes that are eventually no longer radioactive, why are they still around at all? Fascinating question. You seem to have brought your clever pants today. Well, it's fairly simple. Given enough time, all radioactive elements would decay into non-radioactive forms. Even ultra-stable bismuth with its half-life longer than the age of the universe. But elements with short half-lives are around because they were decayed into by elements that recently decayed into them. The chain of decay from the element originally produced in whatever supernova created them to the elements that exist on Earth now lasts billions and billions of years. Also, I should note that some radioactive isotopes like carbon-14 in the atmosphere are constantly being renewed by cosmic rays. Now, radioactive decay occurs when a nucleus has a higher energy level than a potentially more stable version. Typically, this difference in energy is released as what's called ionizing radiation, which you know as radioactivity. It's ionizing because it has enough energy to knock electrons out or add electrons to other atoms, essentially creating ions. There are 3 general types of radioactive decay, each named for exactly what is released from the nucleus as it decays. Let's take a look at what may be the most famous radioactive element: uranium. By far the most common naturally occurring form of uranium is the isotope uranium-238. More than 99% of the natural uranium in the world is in this form. U-238 spontaneously decays into thorium-234 in a process that releases something called an alpha particle. This is called alpha decay, and the particle that it emits is basically the same as a helium nucleus: 2 protons and 2 neutrons. We even describe it that way when writing it. So right away you can see that the math checks out when it comes to the protons and neutrons. 92 minus 2 is 90, and 238 minus 4 leaves you with 234. But you'll note that we don't write the charges. The helium nucleus obviously has a +2 charge, and the thorium atom would have a negative charge as well. While it's not incorrect to write them, these charges are often omitted to emphasize what's going on in the nucleus. Now, alpha particles have relatively low energy. They're pretty heavy as particles go. So while I try not to make a habit of walking around with a hunk of uranium in my pocket, alpha particles can be stopped by nothing more than a sheet of paper or cloth. The second type of radioactive decay is beta decay, which simply emits electrons. It has somewhat higher energy than alpha radiation, but it can still be stopped by a sheet of aluminum foil or even the top layers of your skin. So that thorium-234 that formed when uranium underwent alpha decay, it can continue to decay on its own, and when it does, it undergoes beta decay, releasing an electron and an atom of xenon. Notice that, again, the way we write this is a little different. Even though the thorium emits an electron, we don't use the usual symbol for electrons. Instead, we write it in nuclear notation form with the mass number at the top and the atomic number at the bottom. Since it's an electron and not a proton, we put a -1 for the atomic number. That probably seems a little bit weird right now, but next week when we talk about nuclear equations, you will see why it is useful. The third type of decay is a little different because it only emits energy, not a particle. It's called gamma decay, and it releases electromagnetic radiation similar to visible light or UV radiation, but higher on the energy scale. Because it's just energy, gamma radiation has no mass and contains no protons, neutrons, or electrons, so it's written with 2 zeros. This form of radiation is often released when electrons transition from an unstable, excited state to a more stable state that has a lower energy. That's called the ground state. Depending on how much energy the electron loses, the extra energy can be released in the form of visible or ultraviolet light, X-rays, or gamma waves. Let's take the example of nickel-60. Imagine there's an atom of nickel-60 with one or more of its electrons in an excited state. That's what the little asterisk designates. Atoms can get to this state when they are themselves the products of radioactive decay, or if they get bombarded with radiation from other reactions pushing their electrons into a higher energy level. Now when all those electrons drop down to the ground state, that atom is going to release some gamma radiation. But this kind of transition can also take place where other kinds of nuclear reactions are going on, so gamma decay often occurs along with some other form of decay too. So for example, if that uranium atom is in an excited state when it decays into thorium, it can simultaneously release gamma waves as well as the alpha particle I already mentioned. Now you might have heard of gamma radiation more than the other kinds I've mentioned because it can actually do some serious harm, like potentially turning you into a giant green rage monster that doesn't obey the laws of conservation of matter. Unlike the particles emitted by other kinds of radiation, gamma rays can penetrate your skin, your cell membranes, and ultimately the organelles within your cells. So gamma radiation can not only cause skin burns, nausea, other symptoms we associate with radiation poisoning, it can also alter your DNA, causing mutations and cancer. Okay, but to turn the frown upside down, there's one more type of radioactivity that I am happy to say is really simple. It's called spontaneous fission, and it occurs when an atom simply breaks into 2 smaller atoms without any outside help. This occurs at a ridiculously slow rate in most cases. In fact, the only substance that does it at a rate that's sufficient to serve any purpose is californium-254, and that purpose is to produce neutrons for use in other nuclear reactions. But we'll talk more about that when we go into fission, fusion, and how scientists use and control nuclear reactions. In the meantime, thank you for watching this episode of Crash Course Chemistry. If you listened carefully, you learned what radioactivity really is and about transmutation among elements and among isotopes, and how to make calculations based on an element's half-life. You also learned about different types of radioactive decay, alpha, beta, and gamma, and about spontaneous fission. This episode was written by Edie Gonzalez and Blake DiPastino. It was
All right, there's some more information about nuclear fission, nuclear chemistry. Let's figure out what's going to happen with this unit. Please open up your guided notes. If you go to the Google Classroom page, right above our daily agenda today, you can find your copy of the guided notes. So please open up the guided notes, but additionally, there is a portion of the textbook. If you want to read through that, you're more than welcome to. It's there for you for extra resource. So please open up the guided notes. Our last time, open up the guided notes. Our 11th time, open up guided notes, titling it, all this good stuff for the year. Crazy. Crazy where how far we grown throughout the year, how much we learned throughout the year. Technology skills have definitely advanced throughout this year. Mine have, I'm sure yours have as well. So again, please title it your name. I'm going to put period 6-7. And I'm going to title my name on top. I'm going to date it, just so I have a reference to know where and when we started it. And we will definitely get through topic number 1, notes today. So nuclear chemistry should be an easier topic because it's a lot of proton, neutron, electron talk again. Some topics we saw before, like half-life. You saw that in earth science. Turn this on June 2nd, 2021. What topics are we going to explore throughout the unit? We're going to go through nuclear stability. We're going to go through artificial and natural transmutations. We're going to go through fission and fusion. We'll go through half-life. We'll go through radioisotopes. What topics are fair game for the final? Topics 1, topics 2, topics 3. You'll not see any questions on topic 4, topic 5 on the final exam. So we have a few classes to get through these. We'll get through topic 1, 2, and 3. Again, I'm not reviewing for the final exam because we just reviewed for the post-test. Check this out real quick. We have topic number 1. Topic 1, it's not that long. It's only going to be 2 pages of notes. Topic 1 is 2 pages of notes. Topic number 2 is 2 pages of notes. Again, 2 pages of notes, not that big. And topic number 3, fission fusion, it is 2 pages of notes too. So we will definitely get through this portion before the final exam, which is next Thursday. Let's start off. Let's go right to the top. Let's get right to the nuclear stability. What the heck is nuclear stability? Let's start off by defining radioactivity. So radioactivity, a term that's not going to go away throughout this unit. Radioactivity. Radioactivity, the process by which an unstable nucleus emits radioactive particles or energy. So radioactivity, the process by which an unstable nucleus, emits radioactive particles or energy. If you watched that video, you saw what kind of particles can be released or energy that can be released. He talked about like an alpha particle or a beta particle, or he said gamma energy was released. What's going to make something unstable? What's going to make a nucleus unstable? It's the ratio of protons to neutron ratio. So something that's going to be unstable is the unbalanced ratio of protons. I'm going to rewrite this whole thing. Unbalanced ratio of protons to neutrons. It should be a 1-to-1 ratio. If it's out of that 1-to-1 ratio, then it's going to be an unbalanced ratio. Which elements have a unbalanced proton to neutron ratio? It's elements greater than 82. So unbalanced ratio of protons to neutrons are going to be unbalanced. Atoms with atomic number greater than 82. Atoms with atomic number greater than 82 tend to be unstable, meaning their proton to neutron ratio is not going to be a 1-to-1 comparison. It's not 1-to-1. Really quick, let's just check out the reference table quick again. Periodic table. On the periodic table, elements greater than 82 are going to be unstable. They're going to be radioactive. They're going to tend to be more radioactive. Which elements are greater than 82? Let's just check it out. Here's a periodic table. Hopefully you have a nice big periodic table above your bed by now because you know what that means, this periodic table. A lot of information on it. Radioactive elements greater than 82. The modern periodic table of elements is arranged by increasing atomic number. Here's atomic number 82, lead. Any element greater than lead is going to be radioactive. Has a radioactive elements. So all the orange that are highlighted here are radioactive. Elements greater than 82 don't have the 1-to-1 ratio anymore. It's not like K has 19 protons. It has pretty darn close to 19 neutrons. But when you get further up, the ratio is not going to be in that perspective. Increased number of protons and positive charges in a nucleus tend to be less stable. Next term to define. Next term is going to be radioactive emissions. Radioactive emissions. And there's 4 types of emissions that can be released. Radioactive emissions. Things that are given off. Released emissions, 1M. Radioactive emissions. It's going to be decaying nucleus, decaying nuclei. Decaying nuclei. Releases high-speed energy. So radioactive emission, where a decaying nuclei gives off high-speed energy and particles. And or particles, either or both sometimes. What is released? Radioactive emissions, radioactive particles are given off. And particles. Four types of emissions, 4 types of radioactive decay. Check out table O, or this table behind me. Table O, alpha particle. And alpha particle is going to be the same thing as a helium nucleus. You can look below on the notes too. An electron is going to be a beta particle. Positron is going to be a positively charged electron. And energy is going to be gamma radiation. Gamma radiation has the greatest penetrating power. We'll talk about that more next time. But again, alpha particle is going to be a helium nucleus. Okay, helium nucleus, check it out. Alpha is going to be a helium, boom. Beta particle is going to be an electron, there it is. Positron all the way on the bottom. A positron is going to be a positively charged electron, and gamma is going to be just energy, 0 over 0. Do you remember what these numbers stand for? Again, number on top is the mass, the number on the bottom is the proton number. Mass, proton number. Mass, proton number. Types of emissions, alpha particle, beta, positron, or gamma radiation, or energy can be released. This is a portion of the reference table, table O. You saw that one before. We never talked about alpha or beta, gamma, or positrons before. This unit we will. Scrolling on, identifying which type of particle is given off. How can we do this? By putting an electric field there with a magnet. Opposite charges attract, like charges repel, just like a magnet. Opposites attract, while like charges repel. Repel, 1L. Opposites attract, likes repel. We saw this earlier when we talked about the development of the atom. We went through the experiments that helped derive and make the history of the atom. We talked about Rutherford's gold foil experiment. We talked about Thomson, his cathode ray tube. Within Thomson's cathode ray tube experiment, he took a ray of light, he took a magnet, and he figured out what the electron's charge was. He took a magnet and figured out they deflected up towards a positive. That was an electron. Same thing here in this situation. It's taking a radioactive substance, it's penetrating through a field, and then as it goes through the magnet, the charges are going to deflect in different patterns. The first ray we're going to check out is going to be the orange one. As the orange ray goes through the field, as it goes through the magnet, it's deflecting up towards the positive. This would tell us that the positive and the orange ray is going to have to be negative. Definitely going to have to be negative charge. The one below, the pink one. Next ray, penetrating through the field. It goes through the field and it goes directly right through. Since it goes right through without any diffraction patterns or deflection patterns, its charge is 0. And the one all the way in the bottom, checking out this field, as it penetrates through the field, it hits a magnet and deflects down towards a negative. Since it's deflecting towards a negative, this would have to be a positive charge particle. So you can figure out what the particles are by their charge. You can analyze that. Look at the table above. Oh, alpha particles are positive, beta is negative, positron, there's positives there, protons positive, neutron neutral, gamma is going to be neutral too. So what kind of emissions are here? So double click on the image and we'll label these. We said the positive charge, the orange one's got to be negative, attracted to the positive. Which one's negative? It's going to be a beta particle. The one that's going to be neutral, you click on the box there, it's going to be gamma. And the one below, the one that's attracting towards a negative charge would be positive. Which one's positive? It's an alpha particle, or it could be a positron. Alpha or positron. Make this font a lot smaller because there's not much space there. So please complete that within the diagram. So beta particle, we know had to been negative. Maybe you want to put the charges in here. Maybe you want to say, oh, beta is negative. Maybe you want to say gamma is neutral. And positron had to be positive, or alpha particle had to be positive. Once you're done with that image, you can save and close that image. Hey, it worked the first time. Awesome. The deflection patterns, that you can predict which particle was emitted. The one that deflected towards a positive field, check it out, was a beta particle. Beta was negative. The one that deflected towards, the one that went towards a negative field, check it out, was the alpha particle. Alpha particle is positive. Opposites attract. Another one that went towards a positive field could have been a positron, which is positive. Positive and negative attract. And the one that had no diffraction or deflection pattern is a gamma particle. Gamma ray. Gamma rays, since they're neutral, they penetrate through nearly everything or anything. Since it has no charge, it could easily go through several objects. Okay, moving on. Nuclear energy. We'll definitely explore nuclear energy throughout this unit. With nuclear energy, why is it so important to us? Why is it so important for nuclear chemistry? Nuclear energy gives off a ton of energy. So in this situation, nuclear energy, if you isolate it, if you have it in a chamber or where it could be converted, it will create tons of energy. So radioactive decay gives off a lot of energy. Radioactive decay gives off a lot of energy. Energy is a thing that you're always going to explore throughout life. How are we going to get the most use out of the energy? Cars. Gasoline more effective, or are electric cars more effective? Or which way is the future? Which way are cars going? Gasoline takes a lot of work to get the gasoline from down below, from oring it to the gas pumps. It ruins a lot of the earth. You can explore solar energy, nuclear energy, hydroelectric energy. So many different forms of energy. With nuclear energy, there comes, or radioactive decay comes the mass defect. Comes from the mass defect. Comes from mass defect, where a small amount of a mass is destroyed and converted into a lot of energy. Think of nuclear energy, think of the atomic bomb. That gave off a lot of energy. They used a small amount of uranium to convert that to a lot of energy. Yeah, definitely created a lot of death. But from that, we were able to figure out uses or pros for nuclear weapons or nuclear radioactive particles. Radioactivity. So radioactivity is not a good thing for us. We don't want a lot of radioactivity in our systems and our body. That's why you cannot get so many dental x-rays throughout the duration of a year, or x-rays throughout your body or throughout the duration of a year. You don't want a lot of radioactivity in your body. How could you detect radioactivity? You could check it with photographic film. You could check it with a a light could help you out figure out radioactive particles. You can use a Geiger counter as well to figure out radioactivity. When you buy a home, hopefully you get the house inspected, and hopefully you get a radon test done as well in the basement. A radon test is going to tell you if there's high levels of radon in the home. If there's too high of levels of radon in the house, then it could potentially hurt your cells, your living tissue. It could give you some carcinogens, or could mutate your cells, your living tissue. So there is situations where there's high radon in your houses where they put something called like a mitigation system in there where it filters out all the bad fumes. The last thing for today, I do want to explore this chemical reaction. We're going to figure out how to balance this chemical reaction or fill in the missing link of this box right here. How do we do that? I'm going to double click this image and I'm going to explore this. So here we go. This chemical reaction, instead of doing balancing a chemical reaction like we did in the past, we're going to put let's edit this for a second. You can redraw the equation. A couple of black boxes here. The first thing I told you to do when you balance a chemical equation is put a line down the middle from the reactant to the product side of the equation. But instead of analyzing each element from the reactant to the product side, this time we're just going to analyze the atomic numbers. So in this situation, we're going to look at the atomic numbers. We have 14 plus 4 equals X. You're looking for that. X plus 1. Oh, that's super simple. 18 equals X plus 1. You know that X in this situation is going to be represented by, X in this situation is going to be represented by 17. So that's going to definitely be a 17 there. So 17 up on top. Do the exact same thing for the bottom. So figure out what is on the bottom. You have 7 plus 2 equals X plus 1. Oh, 7 plus 2 equals, you're looking for that missing link right there, X plus 1. Oh, 9 equals X plus 1. What's X equal? X has to be equal to 8. So we have 18 and 17. I'm sorry, 8 and 17. 17 over 8. Let's fill it out. So again, fill it out. We have 17 over 8. You can stretch the text box out so it fits in there. You can make the font smaller too. 17 over 8. What element is element number 8? Anybody? What element is element number 8? Element 8 is atomic number 8 is oxygen. Oh, so that is the last thing I want to complete for today's class. Save and close that image. Hopefully it saves. That's going to be it for today. We're definitely going to explore more of those next time in class. We'll watch a video on radioactive particles too. All right, guys, I know I went through a lot of stuff today. That's it for today's class. We'll pick up on topic number 2 tomorrow. Have a great day. Make some decisions. Bye, Jordan. Have a good one, guys. See ya. Bye, Nadina. Have a good one. Thank you. We'll see you later, guys.